our usual VSET slot. We have Takuo
Recording
Sugaya
in
from Stanford.
progress.
Takuo Sugaya from Stanford, who's talking to us about collusion with optimal information disclosure. This is joint work with Alex Wolitzky. We were supposed to have panelists. I guess it had to happen at some point for reasons under nobody's control. We have no panelists today, so we'll try to do our best to ask questions ourselves, see what happens. Just before a reminder that this is recorded, and just before letting Takuo take over, a reminder that next week, Julia Raslan is going to talk to us about reputation and disagreement in bargaining with imperfect commitment. I just want to also remind everyone that next week, the UK changes time, whereas the US stays what it is, I think. So if you are coming from the US, if you're following us from the US, just make sure you have the right time, because that might, you might find that it's already over by the time you log in otherwise. Okay, Takuo, the floor is yours.
Sounds good. Yeah, thank you very much for inviting me, and thank you very much for joining. I will talk about, I don't know how many joint papers we wrote so far, but one of the joint papers with Alex Wolitzky, and this is about the collusion with information disclosure. So let me start with a broad motivation. So nowadays, there are a lot of, revenue maximizing softwares or price recommending algorithms. Different people call it differently, but essentially an algorithm to collect detailed information from participants in an industry and recommend prices to the participant of the industry. So there are a few examples, and there are, so for most of those algorithms, there are alleged collusion, and the legal conclusion about whether this is legal or not is still kind of uncertain. But, a lot of lawsuits around those algorithms, and I'm not involved in any of those, so I'm completely neutral, but it's just a fact that there are a lot of lawsuits. And one example is a service called RealPage, and that's revenue management software for apartment rentals. So if you have a unit to rent out, you can subscribe the service, and then the algorithm asks you about the location, like how many bedrooms you have, what was the rent for past 12 months, and what's the vacancy rate, how was the turnover, and all those stuff. And then after you put those information in, the algorithm will tell you, okay, in that case, for that unit, you should charge this much rent for next 3 months or something like that. Okay, AI systems do the same thing for retail gasoline. Rainmaker does similar stuff for hotel rooms. And the concern is that a lot of competitors in the market or in the industry subscribe the same algorithm. So for example, for Rainmaker's case, like Hyatt, Marriott, all those kind of hotel chains subscribe the same algorithm, and hotel chains don't talk each other, but they give a very detailed and sensitive information to the algorithm. And so algorithm obviously kind of knows a bunch of stuff. And then the algorithm come up with a price recommendation to individual hotels. And so it sounds a little bit concerning to be honest. And there are sort of like observed increase of the markup. It's not a causality argument, but in terms of the correlation, for example, there's a paper by Sophie Kedawan and Guy Kim about RealPage, and the markets with a higher market penetration rate of RealPage, the markup seems to be higher, for example. Okay, and the defense of those algorithmic services in the alleged collusion is that no, this is just a price recommendation algorithm. Participants are free to just override, especially like undercut the recommended prices if they want to. So we are not doing anything anti-competitive. This is just help you to figure out what's the optimal price, but everybody is free to undercut. So we are not forcing any super markup or anything like that. Okay, so that's where the fact stands. But there are sort of like concerns about increased markup because of those algorithms and potentially reduced consumer welfare. The second point is a little bit unclear because if those algorithms allow firms to tailor prices better according to unknown demand state or something like that, the consumer welfare could be improved. So we do not know, but it seems like a markup went up enough to kind of at least make us concerned that maybe the consumer surplus is also reduced. And we are not making any particular model about a particular algorithm or industry, but our goal is to try to build a kind of theoretical repeated game model with stochastic demand state. And it will turn out that the algorithm knows the demand state and they kind of help participants to coordinate on the equilibrium based on that knowledge. And we built that model to evaluate the effect of price recommendation algorithms. And of course, this is like one particular way to model things, and probably we missed some important aspects of it. So it's just one particular attempt. And yes, you can probably point out 10 different possible details from our model, between our model and one particular alleged collusion cases. But I guess our goal is to kind of at least understand the baseline mechanism behind those kind of phenomena. All right. Any questions?
In your model, there won't be any price recommendation algorithms. That's not the goal. Or
we do actually. We do.
Oh, I see.
Yeah. Or we can call it an algorithm, or we can call it a mechanism designer. I mean, like in terms of the model, it doesn't matter whether it's an algorithm or person. But yes, there's a mediator who has a better knowledge about demand state and recommended prices. Yeah.
Okay.
Yeah. All right. So as I said,
sorry.
Yeah. Yes.
Can I ask kind of
Yeah.
the reverse question that Max
Yeah.
asked, which is,
Yeah.
we know that mediators can allow, they can correlate strategies across individuals and so on. So in a way, that at high level, that phenomenon, if you are going to model things as a mediator, we know that that is possible. Now, whether it actually happens or not, but we know that generally, whatever you can do without the mediator, with the mediator, you can do no worse.
Yeah.
So what is the difficulty here? To prove that you can do strictly better, or something else?
Okay, so probably two things. So I guess one is we try to characterize an optimal equilibrium. So with a mediator. So it's true that the optimal equilibrium with a mediator is weakly better than optimal equilibrium without a mediator. As you said, that's kind of obvious claim. But characterizing the exact optimal with a mediator is not that straightforward. But I guess the benefit of doing this is we could also talk about the consumer welfare side. And as I said, since mediator has a better knowledge about the demand state, it could be the case that the total welfare, the producer surplus, and the consumer surplus all go up. That's possible. And since we characterize the best equilibrium, we could say that at least if we focus on that equilibrium, producer surplus is surely going up, and in fact, we can show that the consumer welfare is going down. So I guess that's another benefit. Yeah. Yeah.
Thank
All
you.
right. Yeah, sorry. Let me just close the door of my office. Somehow it opened up again. So I forgot. This is time of the day that the people come and collect trash. So, all right. And then, as I answered to Max, in terms of the modeling device, it doesn't matter whether mediator is an algorithm or person. And if you know the history of collusion or cartel facilitators, there are some traditional human-based counter facilitators. And one famous example is this Switzerland consulting firm called AC Truhan. And they kind of involved in a lot of alleged collusion. And arguably, what they do is to collect information from participants. Let's say, if you try to form the cartel, and then you kind of send the information about past quarters, prices that you charged, sales that you made, and things like that. And then this consulting firm aggregates those and they come up with a recommended prices, but doesn't share the detailed information about one particular firm to the other firms to kind of facilitate the communication and collusion. So something like that has been happening even in a traditional scheme, but since algorithm can do it with a bigger scale much faster, so I guess that's why there's a kind of like a renewed concern / interest about those algorithms. Okay, so if I write down the full model of what's going on here, this is what I would do if I can solve any model in the world. Supposedly, there's a demand state that affect the demand function, and that is realized stochastically according to some distribution. And then the nature also draws a signal about the demand state, and individual firms observe private signals about the state. And then there's an algorithm or mediator stands in, and they collect a report from individual firms about that signals. And then we put the IC constraint that you need to tell the truth about observed states. And then the algorithm recommends prices privately to individual firms, and we put the enforcement constraint there. Okay, so this is probably the most most direct way to model this. Unfortunately, this model is very difficult to solve. First of all, there are like two constraints, and double deviation could be possible, and all those stuff could be going on. There is a paper by Joe Harrington and others focusing on this IC constraint part only, and assuming that if you subscribe the algorithm, you give up authority to change the price from recommended one. So there's a participation constraint, but once you participate to the mechanism, your constraint is only about this IC constraint, and the enforcement constraint comes automatically. So there's a model like that. So I guess the natural attempt is that what if this IC constraint is not that important, but this enforcement constraint is important. So the other side of the constraint is what we are focusing on. So we focus on enforcement constraint, and we kind of like do it in most relaxed way. In a sense, we a priori assume that the algorithm knows the state without relying on the information from the individual firms. And the individual firms do not receive any signal about the state. That's gonna relax the enforcement constraint as much as possible, because that's gonna minimize the information that the agent has and maximize the information that principal has. Okay, so if you kind of like know the literature about base correlated equilibrium and stuff, it's kind of like in that spirit that we kind of look at the base correlated equilibrium of this game. Does that make sense? Yeah. Okay. So another question when we try to model this situation is, what is the objective of the algorithm? Okay, and there's a paper, again, just another paper by Joe Harrington, and that paper kind of thinks about the objective of the algorithm is the profit of selling such algorithms to the participants. So in that case, the natural way to define the objective is the delta, the difference between the firm's profit when it receives a price recommendation from this service, and the difference between that and when it doesn't prescribe that service and don't get a recommendation. Okay, and under the condition that everybody else participates, so that's a Nash equilibrium. We assume that the participation is naturally happened, and algorithm maximizes the industry profit with the commitment power. Okay, so mathematically speaking, the algorithm is the same as the omniscient mediator, whose objective is to implement the equilibrium that maximizes the sum of all players' payoffs. And if the algorithm can do participation contingent recommendation, for example, if algorithm could say, if 90% of firms prescribe the service, we're gonna start to facilitate collusion, but below that, we don't. Type kind of strategies allowed, then we can actually show that we can incorporate participation constraint. But otherwise, the solution of the model where algorithm's objective is this difference versus algorithm's objective is to maximize industry profit, the conclusion will be slightly different. Okay, so once we see the model, we can come back to this if somebody has a question about this.
Takuo, I
Yeah.
do have a question, but it's possibly something that we want to discuss after your presentation, because I think you're not going to take this into account. But one could think of a regulatory constraint. In other words, the firms may have the incentive not to follow a recommendation, not because they don't believe it's the best thing they can do, but because they don't want to be accused of colluding.
Yeah.
So in a way, you could probably model it as the prices cannot be too similar, or you have to play a mixed strategy. Sometimes you do, sometimes, I mean, you don't have a dynamic, I guess, here, but something like that. And I wonder what you thought about that. I don't think this is in your model, I think, but I wonder what you thought about this.
Yes, so it's not in my model or in our model. There are a couple of ways to kind of incorporate this. I guess there are papers in repeated games saying that, well, with some probability, the cartel is detected, and if it's detected, you need to pay the fine proportional to the difference between super markup equilibrium versus a repetition of static Nash equilibrium and things like that. So, as you said, the detectability maybe, if price is too stable or markup is too high, it's more likely to be detected and all those stuff. That's possible. We don't do this, but I guess that's probably the natural way to model it. That every period, let's calculate a delta between current equilibrium payoff versus static Nash equilibrium payoff, and then we kind of keep adding in with proper discounting. And if that becomes very high, it's more likely to be detected. And once it's detected, you need to pay the fine proportional to that or something like that. And some people put some leniency type kind of incentive in it, that if you are only person who kind of confess you are colluding to the authority, you can be away, you can escape from that fine or punishment and things like that. So I guess you can write a paper on its own, I guess, about that topic. We are not doing that. Yeah. Anything else?
Thank you.
Okay, good. So here's a model. Okay. So if you know the classic paper by Rothenberg-Saloners, repeated game with stochastic demand, ours is very similar. In fact, except for the fact that there is a information design type kind of aspect coming from the existence of algorithm, model is exactly the same. Okay, and we can extend the model, to accommodate a little bit more general framework, but I feel like this framework is probably the best framework to understand the baseline logic, and then we can talk about what kind of generalization we can do without upsetting the baseline logic, and we can talk about it after we kind of learn the what's going to happen with this relatively simple model. Okay. So if you have seen Alex presenting, Alex usually probably post a more general model at the beginning. Maybe I'm teaching MBAs for too long, so I usually like to start with a simple model. Okay, so here's a model. The stage game consists of a typical Beltran competition model with a stochastic demand state. So the set of firms is 1 to n. Demand state is distributed over some compact interval according to some well-behaving distribution function. And let's assume that the demand is IID. We can accommodate Markov switching state and things like that, but IID is easiest. So let's focus on this. at the beginning at least. And then the demand state and the price, let's take them given, then the quantity demanded for the good is S minus P. So this state is at the demand intercept of the linear demand function, and the slope coefficient for the price is -1. All right, so the uncertainty is about the demand intercept, not about the slope. And given the price profile that individual firms charge, this is an undifferentiated Beltran competition with no marginal cost. So that means that the firms with the lowest price receive serve the entire market. Okay, so firms which charge the lowest price receive the payoff that corresponds to the demand. How much was the demand? Like S minus P is a demand, and we divide by the number of firms who charge this lowest price. So you kind of equally split the market among those who charge the lowest price. And the price is P, marginal cost is 0. So quantity times price is in fact a profit. And other firms who charge the price higher than the minimum price will receive a 0 profit because they don't get any demand. Okay, so this is an undifferentiated Beltran competition with 0 cost, where uncertainty is about the demand intercept and the demand is a linear function. Okay. Hope this is clear. And information, yes.
Just a quick question. Hi.
Yeah.
So I understand you're introducing the simpler model first, but my understanding is that the linearity part is probably driven by the fact that when you will introduce the information design stage, you want this, you basically are designing the mean and not the distribution, right? Like, so that is that fair?
Yes, that's fair. That part of generalization is very hard to do. So
exactly.
Yes.
No, it's not about you. It's just the whole literature is kind of.
Yes.
That's the main reason why you're restricting to linear demand function. Right?
Yeah, exactly. So like whether you follow the recommendation or deviate from the recommendation, I guess what matters is the profit is always linear in S. So what matters is the mean belief about S, and beyond that, conditional distribution of S given the information that you have doesn't matter. And so I guess that's going to reduce the dimensionality of the space that we need to work with. And yes, that's important. That's important. Yeah. And you can also allow incomplete information about the cost, like supposing that there's a common cost component, like a reserve price is not known, and they are participating in a procurement auction or something like that. That's fine. It essentially becomes kind of isomorphic, whether you put imperfect information about S or incomplete information about the cost. That's pretty much the same. But linearity is again important, right? Okay. And then given the history, what happens? Well, the state is IID, so it's drawn IID from the distribution function. And then the algorithm observed state S. And as I said, other firms don't receive any signal at this stage. And we can allow, so technically speaking, right, this is with loss of generality, but we focus on the case that the algorithm send a public message to everybody. Okay, there's a possibility that the private messages can do better because in that case you can do correlated equilibrium rather than So I guess the reason why we focus on the public message is private message is already a little bit complicated, even without demand state. So Howard Norton, Alex Wolitzky, and I have a paper about repeated Beltran competition, and there's an algorithm who can send private messages, and there's no demand state. Okay, and even without the demand state, the solution with a private message is already kind of complicated. And when we wrote that paper, we thought about a little bit about incomplete information about the demand state. That model is very untractable. So to make progress, we make an assumption that message is public. So algorithm needs to send the same message to everybody. All right, and this is potentially with loss of generality. So it's for tractability reasons, to be honest. Right. And then firms update a belief about S, and as Rohit said, that what is important is mean belief. So when S is distributed according to F and M is distributed according to some strategy sigma given S, when you observe M, you can base update and calculate the mean belief. And the given linearity of the payoff function, mean belief is what matters, as we're going to see. So that's what we work with mainly. Yeah. Yeah. Okay, so in repeated games, what are the history? So the complete history is state, message, price profile, state, message, price profile, state, message, price profile, and so on. And the algorithm observes this entire history, okay? On the other hand, individual firms don't observe S. So they observe a message and the prices, and that's it, right? And as I said, message is public, so everybody observes the same M. And algorithm's history, strategy is a mapping from the history up to POT and today's state to a distribution of messages. And let's use sigma to denote that strategy. And firm-wide strategy is a mapping from firm's history and the message to a distribution of prices. Yeah. Yeah. Yes. Yeah. It doesn't matter so much because at least for this IID model, inference about the past state and the stuff is not really important. So only thing that matters is whether somebody has deviated or not. And once it's deviated, since it's undifferentiated Bertrand, implementing minimax punishment is very easy. And as long as the algorithm observes it and they flag it, then it really doesn't matter whether firms observe prices or not. So that's in reality it could matter, but for given this particular model, it doesn't matter in that sense. And so the repeated game, like at the beginning of the repeated game, the algorithm commits to a repeated game strategy sigma, all right? And then given sigma, we kind of like pin down the environment in which firms play this game, right? And so given once we fix the strategy of the algorithm, we can calculate the set of sequential equilibrium of this game. And we select an equilibrium that maximizes a discounted sum of the industry profit or sum of everybody's profit. Okay, and then another caveat is we also focus on pure strategy equilibrium. And this is again potentially with loss of generality. Why? Because supposing that discount factor is not super high, so sometimes IC constraint is binding when we try to implement monopoly price all the time or something like that. Okay, in that case, if we allow firms to mix actions or prices, then when I try to deviate, the most tempting thing to do is to just undercut other firms so that the markup is highest and I capture the entire market. But if other firms mixes on path, then I do not know which price allows me to just undercut the opponent. Okay, so if we allow mixed strategies on path, it's gonna reduce on path payoff, but it also reduces the deviation gain as well, because now if I try to deviate and undercut other firms, I do not know which price allows me to just undercut other firms. All right. So taking that into account, it's possible that mixed strategy equilibrium is potentially improves what we can do with pure strategy equilibrium. But again, the excuse is that mixed strategy equilibrium is arguably harder to figure out what's optimal compared to correlated equilibrium, because correlated equilibrium is a linear programming where mixed strategy Nash is not. And in the paper with Alex and Juan, we already figured out that without state, correlated equilibrium is hard to characterize. So with state, mixed strategy equilibrium is probably even harder to characterize. So we assume a pure strategy for the tractability reasons. Given that said, so once we focus on pure strategies, then given strategy sigma, we can conceptually characterize the set of sequential equilibrium, and then we assume that the firms coordinate on the one that maximizes the joint profit, and let V sigma be this equilibrium payoff that maximizes industry profit among all equilibrium strategies. And we assume that the algorithm commits to sigma that maximizes this V sigma. So rationally expecting that the firms will coordinate on the best equilibrium given algorithm strategy sigma at the beginning of the game, algorithm commits to sigma that delivers the highest equilibrium payoff. That's okay? Question?
So should I think of this as like the algorithm, like we're trying to play a base correlated equilibrium where we're picking
among pure strategies, yes.
Amongst pure strategies, where we're going to pick the one possible point in the feasible set, which is the joint maximization of profit, and we'll do it every period for the value function. Like it's like kind of without commitment.
Yeah, for the value function, for the value function, but since this is a pure strategy and the state is IID, in fact, the optimal thing to do is on pass, you do the stationary thing. And off pass, you kind of, so I guess the line of the argument is pure strategy, IID environment, then actually we can say, we could potentially like alternate, like today you serve the entire market, tomorrow I serve the entire market and things like that. But those things are not efficient. We could prove that it's going to improve the on-pass payoff and without violating IC constraint to construct. So, okay, sorry. We can construct some stationary strategies that makes everybody better off in the Pareto sense without violating IC constraint. So that means that we can focus on the stationary strategies. And once we focus on the stationary strategies, if S is IID, then the sigma is IID as well. On path at least. And if somebody deviates, then we go to the punishment phase. But since this is undifferentiated Bertrand, punishment is Nash, so that's very easy.
And just one conceptual question. So
I
mean, I'm not a legal expert in this, but from what I understand by reading Harrington and others is that they regard algorithms to be kind of a novel, let's say, a problem for policy and law, because they say that you cannot really explicitly prove in a court of law that Takuo and I were trying to collude. But like, but if the algorithm itself is explicitly maximizing joint profits and is public, right? Then I could probably these guys could probably take us to a court, right? So
okay. So right. So as typical of the information design, I guess the optimal strategy of the firm is just a selective disclosure of the demand set.
I see.
And if it's used in an optimal way, then that's going to maximize the joint profit. But algorithm could say that we are just selectively disclosing certain part of the state, and we could argue that that's probably not is a little bit anti-competitive, but the message itself doesn't have a direct element that you should collude and stuff, I guess. But
I'm just getting carried away with the recommendation. You're right. You're saying it's just any disclosure policy just so happens that it'll I see.
Yeah. I mean, that's a typical issue of the deviation principle as well, even if it drops the pure strategy argument, right? Because we do not need to say literally that you should collude with this price. You could say something and that is encoded in people's minds that we should do that. But you're right that if it's an algorithm and it's directly going to the online pricing platform or something like that, it's probably easier to catch, maybe. So yeah, that's possible. All right. Good. Although we talked about incomplete information, I'm going to start with full information benchmark, meaning firms observe S and no algorithm. Okay, and we focus on pure strategic equilibrium. Why we do this? Because once we understand this, we can combine this way of solving repeated game and information design type kind of technique, and we can kind of like combine those two, then we can solve our original problem as well. So that's why it's probably good to talk about how to solve the complete information benchmark. So suppose that S is IID across period, but everybody observes S. Okay, and there's no algorithm there. And we focus on pure strategic equilibrium. Okay, and I guess I already said this while I was answering to Rohit's question, but since this is symmetric Bertrand competition, on-pass price is stationary as a function of S in optimal equilibrium for the firms. Why? Because we could like rotate like today I get the full market and tomorrow you get the full market and things like that. But there's a discounting. So I guess your IC is more binding because you need to wait until tomorrow. And my IC is a little bit relaxed because I can get full market today. So if IC is binding, then we would rather charge the same price today and tomorrow and split the market equally and average out our IC constraint. And when one is more binding and one is less binding, averaging out is the best way to do this because we need to satisfy everybody's IC constraint, right? So that's why we can prove that at least within the pure strategy equilibrium, the best equilibrium is stationary. And so then things are very easy, right? The best equilibrium with stationary strategy solves the following value function problem. Let's call V as a per firm optimal profit. And then what is it? That's equal to, so state S is jointly draw according to F. And we could assume that it's a stationary. So whenever S is drawn, everybody is trying to coordinate on price, which is a function of the state, and equally splits the market. So individual firm get the pie divided by N. By the way, this pie is the industry profit, the price minus demand intercept minus price. So this is quantity, and this is markup because cost is 0. So this is profit, right? So everybody gets 1 over N times industry profit. And then since everything is IID and stationary, so tomorrow you get the delta times V as well. All right. And there's IC constraints that this coordinated price P, if you follow that and tomorrow you get the delta times V is better than you undercut the current price P and get the entire market today. And then we go to the punishment base and get the minimax value 0. All right. And the minimax is Nash now. So it's very easy to implement. Okay, so this is a characterization of optimal equilibrium with full information benchmark. Is that clear? So this is exactly the same as Rotenberg-Salona, by the way. So if you are familiar with that paper, it shouldn't be a surprise. Okay, and then main message of Rotenberg-Salona is, I guess, in terms of their phrasing, is price wars during booms. And what does it mean is that since demand is IID, if today's state S is very high, then today looks very good and tomorrow looks worse than today, right? So that means that the pie that I get when I deviate today is very high when state is high, but the continuation payoff is always constant because state is IID. So that means that I have a higher temptation to deviate from the coordinated price when state is high. Okay, so when the discount factor is in intermediate range and IC constraint binds after a certain state, then when it binds is when state is high. And if that happens, then you need to coordinate on a lower price to satisfy the IC constraint. And that's what they say price wars during booms. Okay, so mathematically speaking, the deviation gain is like this minus this, all right, is increasing in S for all P. So if IC is binding, then this needs to be equal to delta V, right? So I guess this is IC constraint. If this binds, then this needs to be equal to delta V. That means that when S increases, left-hand side increases, right-hand side stays the same. So to satisfy IC constraint with equality, P needs to go down. Okay, so in the region where IC constraint binds, S goes up, PS goes down. And that's what they mean price wars during the boom, because it looks like as they start a price war, although they are coordinating on the best equilibrium. So it's not really a price war, but it's, yeah, I mean, that's one interpretation. All right. Why I mention this? Because I'm gonna contrast what's gonna happen if we design the information later, and the price wars during the boom doesn't happen if we design the information. So we're gonna talk about it later as a comparison. For later use, when we solve the information design problem, it's gonna be useful to what is called to manipulates the problem a little bit. I mean, if you have worked on repeated games and if you see something like this, there's almost like an immediate reaction of, this is what I want to do, is to subtract delta V from both sides and divide 1 minus delta from both sides to get this. You know, like if we bring this to the other side, we get 1 minus delta times V. Divide both sides by 1 minus delta, we get V is equal to this without that 1 minus delta term. And then we consolidate everything depends on pi on one side and everything depends on V on the other side to write down IC constant like this. It kind of makes sense, right? Because the demand is IID, so on average, what you get is on average what you get per period, and this is what you get per period. And IC constraint means that since we are splitting the market equally, the pie that I'm eating cannot exceed a certain number, because if I deviate, rather than I share the entire pie with everybody else, I can eat it by myself. So that means that when the pie is too big compared to V, I want to deviate. So that's why this is a proper way to write down IC constraint. All right, so move up this problem up there now. So if this constraint is not binding, we want to maximize this. So we should coordinate on a monopoly price, right? So if this is binding, we should coordinate on P such that the P is equal to the monopoly price given S. For S, where this binds, then this 1 minus, then like we should coordinate on P so that this constraint holds with equality. So that means while this is not binding, we should focus on, well, we should coordinate on the monopoly price. If this binds, then this holds with equality. That means that this term is equal to that term. And in fact, it means that this term is equal to that term. So taking that into account, we can write down that the V is equal to, yeah, maybe we should use this. Yes, and then when this is not binding, then we focus on the monopoly price given set S. And if it's binding, then this is equal to that. And so we can replace this instantaneous payoff with this binding IC constraint. And so we get that. So now it's relatively simple, right? V is equal, I mean, still a fixed point problem because V shows up on both sides. But we can say that the V is equal to the expectation of the mean of those two. All right. And then we can write down the picture. Supposing we know what is V, how this function look like. Well, the monopoly price, monopoly profit given S is an increasing function of S. Why? Because fixing price, profit is linear in S. So if you don't react prices to the state change, the profit is linear. But monopolist is optimally reacting to the state change by adjusting the price optimally. So that allows monopolists to increase the profit even faster than the linear case. So that's why we get the convex monopoly profit. And this is just constant because V is constant. So we get minimum selection of these two lines. So we get this and that. And Rothenberg-Saloner's price war during the boom is up to this point, IC constraint is not binding, so you should charge monopoly price, which is linear in state. Once we hit IC constraint binding, then price starts to need to decline because we need to satisfy this IC constant with equality, and if S increases, P needs to go down. Okay. So that's the summary of Rotem-Barcelona. Okay. Good. So why we did all this is that once we understand this, it's relatively straightforward to understand what we are supposed to do. Before that, as we discussed before, given the linearity of the payoff with respect to state, what matters is a distribution of the mean belief, a given message. What's the mean? What's the conditional mean of S? And so I guess natural thing to first figure out is that what is a set of implementable distribution of mean beliefs, and we kind of already know that that's a mean preserving contraction of original distribution F. Why? We can think about this. Right? When we reveal S truthfully, then distribution of M and the distribution of S becomes the same, like it becomes the same. And given the message, you know S. So then mean belief distribution will be exactly the same as F if we reveal S truthfully. Revealing some intervals or pulling some extremes and the stuff will kind of make mean belief less diversified compared to true S. Right? So that means that the distribution becomes mean preserving contraction of it. So that's why the distribution of mean belief is implementable if and only if that is a mean preserving contraction of F. In other words, if we kind of look at the belief that the firms own, and if you look at the distribution of G, the true state distribution is mean preserving spread of the distribution of mean belief owned by firms, because algorithm knows true F while firms know only, deducted version of it. So that's why G needs to be a mean preserving contraction of it, or the other way around is F needs to be a mean preserving spread of G, because F should be always more informative than G. Yeah. So yeah, so this is a very typical argument in information design. And then given the mean belief, structure of the game is the same as Rotem-Barcelona. In a sense, in Rotem-Barcelona, we kind of interpreted this S as like a realized state S. But if we can think about this S as, firms get the same information that leads to their mean belief being equal to S in Rotem-Barcelona, nothing changes because everything is linear in S. Right, so the one interpretation of Rotem-Barcelona is everybody observes S directly. The other interpretation is everybody get the common signal about the state, and given the state, the mean belief given that the signal is equal to S, and we just use, given the signal distribution, the distribution of mean belief S is equal to F. We can kind of interpret Rotem-Barcelona that way. If we interpret Rotem-Barcelona that way, then what we should do if algorithm can design the information is, now we see this S as a realized mean belief now. And previously S was distributed according to F because that was not the design variable. You get a signal about a state, and S is a mean belief given the signal, and given the signal distribution, the distribution of the mean belief S was F. That was Rotem-Barcelona. Now we can design the distribution of the mean belief, and as long as that the mean belief distribution is mean preserving contraction of F. So since everything is linear, so let me say this again because this part is probably the well, once we understand this part, the rest is relatively straightforward. Okay, so since everything is linear, we can interpret Rotem-Barcelona model where such that, the true state nobody observes, everybody get a common signal about the true state. Let's write down S as a realized mean belief about a state given signal S, and the signal S is distributed according to F. We can interpret Rotem-Barcelona that way because everything is linear. But if you take that interpretation, if you can design the information, then what you can do is to see this S as a realized mean belief given the message from the algorithm. And the algorithm can implement a distribution of the mean belief as long as that distribution is a mean preserving contraction of f, the distribution of the signals that that algorithm has. Yeah. Let me stop. Any question? I guess from now on, what I'm gonna do is to solve property of this optimal information structure, and then talk about the implication on consumer surplus and stuff, if there's no question.
So, Takuo, I have to go in 5 minutes. Just a conceptual question. So when you showed that graph of the price, I'm guessing what you want to do is kind of relax
this one?
the incentive constraints at the
and
so instead of entering that price war, you could just use information, right, and try to pool states at the top.
Well, why don't I show you the
So,
optimal? Let me just probably tell you. I'm gonna go through the proof, but at least at this point, it's probably good to tell you how the information structure will look like. So fix V. Okay, so guess V. Given that guess V, the optimal distribution follows the following form. That this is the same picture as Orton Barcelona. Of course, the value itself is different because now we have a maximization operator here. But given V, it looks the same. Let's call S star being the state where price war would have started if we don't do anything about information design. And then let S hat be the threshold of the state such that if we pull the information or pull states above S hat, conditional mean belief of S is exactly equal to S star. And what you want to do is to disclose everything below S hat and pull all the information among S hat. So Lloyd is right that previously price was going up like this and then going down. Now we kind of pull information so that given the mean belief, you always charge monopoly price. But here, you are kind of pulling information. So given compared to the realized state, you are potentially charging the price higher than or lower than the monopoly price given the realized state, but you do not know because algorithm pulls it. I guess, and then what was the question?
Yeah, that was I was just trying to get the intuition. So, and then one quick question is that, sorry, I'm derailing you a little bit, but it doesn't seem, the linearity to me seems more important than the undifferentiatedness, right? So if I just had two firms, right, like, and they had, let's say, a probabilistic demand function, but at least it was parameterized as being linear. This should still go through, right?
Yes. I guess, the differentiated Beltran with linear demand function should be fine.
Yeah, I see. Okay.
Yeah. So, and okay, so let me give you a quick proof of why this is the case. I'm gonna kind of draw the augmented function, and let's call it good. So okay, so I guess let's call this strategy to reveal everything below S hat and pull everything above S hat as like a green strategy because that's gonna give rises to the value distribution like this, and then Dirac measure at S star. So let's call this green and the G star. That's what that's what this is. All right, and the proof of why this is optimal is this achieves the same value as the following information design problem, rather than this mean of these two functions as an objective, but objective is this red line that goes along with our objective function and then draws a linear line between this point and that point and keep going up. All right. And then this red line and then the red curve is globally weakly above our objective function because here it's the same, here it's strictly above, and then here the mean is this part, and the red line is going up, right? So this red line is globally above our objective function. So if a value according to this green dot and the green line is the same as the maximize information design value given this red line objective function, then we are done because that's the upper bound. But then, like since this red line is a convex function, so one optimal strategy is to reveal everything, no? But this part is linear, so it doesn't matter whether you reveal everything here or you only reveal a mean BF S hat. No, S star, sorry. So if you just follow the same disclosure policy as G star with a red line, that's optimal if the objective is a red line. But then, given this optimal disclosure policy G star with a red line, what you implement is revealing here or here and then achieve this point, given the linearity of the red line of this. So that means that this G star is optimal for this red line and achieve the same value as what you can achieve with this original objective function. But then the original objective function is globally below this red line. So if you achieve the information design optimal of the red line with this globally lower distribution, lower function, then we are done. So that's a proof. Yeah. And this is a very typical proof of the information design. Like if it's a convex function and then concave, then linearly extrapolate convex part and then following those kind of logic to prove that this what they call upper censorship is optimal. Yeah. Okay, I probably should wrap up soon. So Rothenberg-Salona suppress price to satisfy IC. And here the algorithm design information to satisfy IC. So it would be less efficient to change the price less than monopoly price given mean belief. You would rather design the information so that the given the information and the given mean belief, it satisfies IC to charge monopoly price. That's what you're supposed to do. Okay, so given the mean belief, price is always monopoly priced. However, since you're pulling information here, price is higher than the monopoly price given the realized state because here state is lower than S star. So if you charge monopoly price given S star, you are kind of charging the super monopoly price, even higher than the monopoly price given realized state. Here, the price is lower than the monopoly price. All right. And then the last part is consumer surplus. All right. So if algorithm knows more about the state, then what happened to consumer surplus? Is that bad or good for consumer surplus? When I say about, as I said about Rothenberg-Salona's model, we can model this algorithm knows more as a mean preserving spread of this underlying distribution F as well. Why? Because we can think about this distribution of F is a distribution of state, but we can also interpret this distribution of S is belief that the algorithm has given the signal that the algorithm get from nature. And when the nature signal gets improved about state, then we can interpret this as a mean preserving spread of F itself. All right. So then the set of implementable distribution of mean belief, mean preserving contraction of F expands. Because if we take a mean preserving spread of F, the previously possible mean preserving contraction is still possible. So this means that the algorithm has a higher freedom. And we can prove that the consumer surplus is decreasing as long as consumer surplus is concave up to transformation, which means that the consumer surplus can be written as some linear function of S and the price, and then the other parts that only depends on price and the other part that only depends on the state. And this part is concave in S if we plug monopoly price in there, okay? And why the shape of this part doesn't matter? Because this part directly depends on the state, and even if you change the disclosure policy about S, this part is a direct effect of state to consumer surplus, and that you cannot design. So what matters is only the effect of the designing the information through prices. So that's why this part is the only thing that matters. And we can prove that the concavity assumption holds with linear demand. So then the consumer surplus is concave up to transformation, then the mean preserving spread of F reduces consumer surplus in equilibrium. Why? Well, given the optimal information, the firm charge monopoly price, as I said, right? So it's kind of intuitive that if firms do monopoly stuff, if I give more information to monopolist, it seems bad for consumer surplus. When consumer surplus is a concave function of the monopoly price and the state, that kind of makes sense. We need to be a little bit careful because this cutoff price is hard. It's also changing because value changes and the information changes. However, we can prove that nonetheless, we can actually prove that the consumer surplus will go down. Okay, so let me skip extensions and let me conclude. So what we do at the mathematical level is to combine the information design and collusion. And optimal information structure is upper censorship. And the price is rigid during booms because we pull information. So there are a lot of realization of state with which you charge the same price when we charge, we pull the information over there, and more information to the algorithm reduces consumer surplus. Okay. We can think about the future research, objective. Other objectives, algorithm, private messages, all are all important, but could be more complicated. In general, what we do is a stochastic games or a repeated game with incomplete information with information design. And the trade-off is relatively clear, right? To increase on-pass payoff, we want to reveal more information. For example, in today's game, if we reveal more, firms can have an feasibility to coordinate on the monopoly price given the real state. That increases the on-pass payoff if IC constraint is not binding. But this allows more tailored deviations that, when we are in a boom, I want to deviate, otherwise I don't. And if we pull the information, you cannot tailor deviation as much, and that's going to reduce the deviation gain. So there's a trade-off that on-pass, if you reveal more, it's good, but off-pass, deviation gain-wise, revealing too much is bad. And Alex and I have been working on a paper related to this topic in the context of private monitoring and other cases, but this is kind of like a very general statement, and we kind of believe that there are probably more intuition can be squeezed out of this general property of the incomplete information game with information design as well. Okay, so that's it.
Yeah,
I guess we don't have a panelist, so I guess
I was trying to think of something and I forgot that I was the host. So it took me a few seconds to change shoes. So I might have some questions, but I want to open the floor to other people first. If anybody wants to just unmute themselves and ask a question, that's going to be fine.
You go ahead first, Francesco.
Okay, I'll
break the
ice. I'll break the ice. So let's talk about private monitoring and private monitoring. So I mean private messages.
Yes.
So it's not obvious to me how, and I'm probably, this question comes just from unfamiliarity with the literature. So what's going to happen to the possibility of punished deviations if we allow for private messages?
Right.
Are we going to think of the algorithm essentially assigning punishments so that in a way, certainly in reality, there's what now we call credibility problem. You have to trust that the algorithm is punishing people when they ought to be punished and not doing something else.
Yep.
But certainly the punishment has to go through the algorithms, through the algorithm, right? They cannot really be observed because you don't want what the algorithm recommends and so on. So I appreciate you told us that this is very hard to do. So I guess I'm only asking for guesses and intuitions and conjectures.
Good.
What do you think that does? What do you think that does to incentive compatibility? In other words, I suppose.
So so I guess there are probably two ways to answer your question. One is supposing that we kind of want to write down the tractable model to capture private monitoring and punishment, what we could do. And this is kind of in line of what we did with Juan Ortner, that in that model, we consider static correlated equilibrium with undifferentiated Bertrand with no incomplete information. So very simple stage game. But the mediator or algorithm has an ability to punish somebody who didn't follow the recommendation up to the stick X. Okay, so X, so the punishment could be either 0 or somewhere between X. And if I recommend you price of P, and if you charge some price different from P, then I can reduce your payoff by X if I want to. So that's a model with Juan Ortner. And what's going to happen is that sometimes I would supposing that we two play the game, okay? And then sometimes the algorithm asks you to mix according to the certain distribution, so that I'm indifferent between following the recommended price or like undercutting the recommended price. And since you are kind of mixing according to the exponential distribution function or something like that, even if I undercut, I have a higher probability of winning against you, but the probability doesn't jump discontinuously. So with a pure strategy, I know exactly what price you charge. So if I deviate, my deviation gain jumps from, or like my probability of winning jumps from, sharing the market to I capture the entire market. And if you kind of mix, then if I deviate from the recommended prices, my probability of, or my demand will go up, the quantity demanded go up, expected quantity demanded will smoothly go up, but my markup will go down, right? Because I'm kind of charging lower prices. And the distribution of recommended prices to you is designed such that those two effects exactly cancels out, basically. And so that's what happens if we write down the simple model of correlated equilibrium with mediator having an ability to punish the deviator. And the other way to answer your question is that what's going on in reality. And in reality, if I look at the litigation documents about real page and the stuff, it seems like what's going on is that overwriting the recommended price of the real page, there's a bit of the hectic cost, like hassle cost of doing this. So previously, I guess what DOJ argues is that supposing that the big, apartment management company owns a big apartment, and then headquarters do not know exactly what agents do on the ground. And the agent give a secret price cut in terms of, if you sign the contract today, the rent for first few months is free, or things like that. And those kind of price cut was kind of like went through without being checked before they subscribe real page. But once they subscribe real page, since revenue management software is integrated with real page's recommendation, if somebody overwrite recommended prices somewhere along the decision chain of the organization, then it's going to be flagged everywhere on that chain. And then the management starts to realize that, our agent on the ground are giving a lot of secret price cut to the consumers, and let's make it harder. And so there's a document in a litigation saying that if somebody needs to override the price recommended by the real page, then automatic notification goes to that person's boss. And you need to write down the explanation documents to their boss that this is why we are kind of lowering the price compared to recommended prices and stuff. So in reality, there's a hassle cost of overwriting the recommendation. So I think your intuition of punishment, whether it's going through the prices or whether it's going through the hassle cost or some organizational punishment, I'm not entirely sure which one is the most relevant ones, but definitely there is a cost to undercut the recommended prices for sure. Yeah.
Okay. Did I break the ice? Because I have more, but
yeah, you broke the ice. I have a question.
Yes.
Okay.
So it's about what's observable here for a third party, like an authority or something. I mean, in Rottenberg and Saloner's paper, you just, to test the theory, you have prices and demand shocks, and you can check if this behaves according to the prediction of the model. In your case, one of the variables is the disclosure policy, which is probably hard to observe. You had a slide about what it implies for the prices just before the consumer surplus. Could you kind of rehearse what is observable? Is it testable?
Right. So I guess first of all, once we have enough data about quantity and price, retrospectively we can back out a state. Maybe it's stochastic, but before you charge the price, you do not know. But once you charge the price and the quantity is realized, you can at least infer what was the state. So probably the econometrician can back out what would be the implied state, and then our implication of our model is that first of all, the state is weakly monotone in the state, and there are regions where compared to the realized price and the realized state and the monopoly price given that realized state, there's a region where price is higher than the monopoly price, and there's a region where the price is lower than that monopoly price. So I think if we have data about quantities that is realized after you charge the price, we should be able to test this. Yeah.
Thanks.
Okay. Anybody else?
Mm-hmm. 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 Sure. Mm-hmm. I see. Although right now the IC constraint holds with equality here, right? So I guess if there's a small, so there's a small probability that somebody is as undercutting, then IC constraint would be violated potentially, and also, yeah. That's true. It's not, it's not obvious. Yeah. That's possible. I guess another thing we need to check is that if there's a probability that this part is stochastically revealed to me, if it's not revealed, then actually my belief will go up, and then like I see constraint it starts to bind. So I guess we need to do something about that. So that part is probably hard. And the bottom part, I agree that it's kind of in line with this like a mixed strategy makes it harder to come up with optimal deviation type kind of argument together with the fact that all firms are charging the super monopoly prices. And so, I mean, we can think about, is there any like a epsilon type kind of arguments that is give us a first order improvement or not when epsilon is sufficiently small? Yeah. Thank you for the suggestion. Yeah, I think that's good to check, I think. Yeah.
Okay. I would first of all stop the recording because we're 15 past. I guess, Takuo, you said you have 5 more minutes, I suppose.